Hello, good morning. I am Seema Garg, Associate Professor in Chemistry, SPC Government College, Ajmer. Today, lecture 9 is about degrees of freedom, Hooke's law and characterization of IR. Degrees of freedom. In the molecule, all the atoms have 3 degrees of freedom on Cartesian axis, x, y, z. So, atoms N will have 3n degrees of freedom. Number of fundamental vibrations. For linear molecules, formula 3n minus 5, and for non-linear molecules, formula is 3n minus 6. For example, carbon dioxide, carbon disulfide, these are the linear molecules. So in carbon dioxide and carbon disulfide, 3 atoms. So 3 multiplied with 3 minus 5, 9 minus 5 is equal to 4. So total 4 vibration modes in carbon dioxide. Similarly, carbon disulfide also containing 4 vibration modes. HCl. In HCl, 2 atoms are there, hydrogen and fluoride. So 3 multiplied with 2, 6 minus 5 is equal to 1. So in HCl, 1 vibration mode. For non-linear molecules, for example, methane, CH4. So total number of atoms 5. So 3 multiplied with 5 minus 6 equal to 9. Here n minus 1 stretching vibrations means 5 minus 1 is equal to 4. 4 are stretching vibrations, whereas 2n minus 5, 10 minus 5 equal to 5. So 5 are bending vibrations. So total number of vibration modes are 9. 4 are stretching and 5 are bending. Symmetrical molecules like hydrogen, fluoride, nitrogen, they don't have dipole moment, so they do not absorb in the IR region of the spectrum. Vibrational frequency. The frequency of vibrations is directly proportional to the square root of the force constant of the bond. The vibrational frequency of a bond can be calculated by using the Hooke's law equation. The frequency is equal to 1 upon 2 pi c upon k under root k upon mu, where c is the velocity of light, k is the force constant of the bond in dynes per centimeter. It gives idea of bond strength. If bond strength is more, frequency will be more. And if mass of reduced mass will be less, frequency will be less. So it depends on the mass of the atom and the force constant of the bond. For example, carbon-carbon triple bond, it having frequency at 2100 inverse centimeter, whereas carbon-carbon double bond having frequency at 1650 inverse centimeter, carbon-carbon single bond having 1000 inverse centimeter. Here Ma and Mb, both atoms having equal mass, means carbon, in all 3 having carbon. So it depends on, frequency will now depends on the bond strength of the molecule. In this series, carbon hydrogen and carbon deuterium. Carbon deuterium having more mass compared to hydrogen. So here K is constant, but Mb is increasing. So vibrational frequency will decrease. So here carbon hydrogen having frequency at in the range of 2800 to 3100, whereas CD having 2200 milliocentimeter. Similarly, OH and OD. In OH, frequency is 3570 milliocentimeter, whereas OD having less frequency 2630 milliocentimeter. Similarly, electronegativity also responsible here. In this series, mass of MB is increasing, K is constant, and MA, see here, mass of MB is increasing, and MA and means carbon are constant and K are constant. So frequency will decrease. Selection rule. Infrared light is absorbed only when a change in dipole of the molecule takes place. Carbon dioxide, if having symmetrical stretching, dipole moment is 0, then it is IR inactive. Asymmetric stretching absorb frequency at 2350 inverse centimeter, it is IR active. Bending vibration in carbon dioxide, it also gives frequency about 667 inverse centimeter. If a molecule has a center of symmetry, then the vibrations are centrosymmetric and are IR inactive but Raman active. Vibrations which are not centrosymmetric are IR active but inactive in Raman spectra. Intensity and position of infrared absorption bands depends upon the distance between dipole moments of the molecule in the ground state and the excited state. Infrared IR is most informative because functional groups are not centrosymmetric. The absorption bands may have strong, medium, or weak intensity. Here, means weak having lower height, and medium having comparatively higher, and strong having long percentage of absorption band. The IR spectrum is recorded as a graph of the intensity of transmitted or absorbed IR radiation. The frequency of infrared absorption due to stretching or bending vibrations by a molecule depends upon the following factors: the relative masses of the atoms, the force constant of the bonds, the environment or geometry of the atom. For example, see this molecule, acetaldehyde molecule, right? Here, in acetaldehyde molecule, see this carbon-carbon stretching, 1165, here carbon-hydrogen, right? It is close to carbon-oxygen, so its stretching is different, means having this stretching is slightly lower frequency, 2720. Whereas in this molecule, this CH group, CH stretching is higher, 2870 inverse centimeter. And this CH3 bending also occur at 1460, and the CO stretching is a strong peak. It is observed at 1730. So these are the frequencies observed in acetaldehyde molecule. Because we know This bond dissociation energy of carbon hydrogen is 104 kilocalorie per mole. Carbon carbon bond dissociation energy is 88 kilocalorie per mole. Due to this reason, carbon carbon frequency bond means this is weak. It is a weak stretching, whereas this carbon hydrogen is strong. Classification of bands here. Here. This type of in certain cases like amino, primary amino, it will give you doublet type of thing, right? It is a big narrow band. So these are the big singlet type. Medium is slightly higher, right? And sharp having more higher. So this is in between the graph means I want to show you what types of peaks are observed in the molecule. Broad, narrow, medium, weak, strong. IR absorption range for identification of functional groups. See here. Here. This 600 to 1400, it is also known as a fingerprint region, and we also call it single bond carbon carbon region. Here stretching frequencies of carbon carbon, carbon oxygen, carbon nitrogen observed. Whereas in this 1600 to 1800, it is called double bond carbon carbon double bond region. Carbonyl, carbon carbon, carbon double bond nitrogen, like that stretching frequencies are observed. Whereas in 2200 to 2400, triplet bond, carbon carbon triple bond, carbon nitrogen triple bond, peaks are observed. This is called hydrogen region because it is frequencies of NH stretching, OH stretching, and CH stretching are observed. So this is the outlet of certain functional groups observed. This is the table list of certain frequencies. See here, hydroxy group, primary alcohol, secondary alcohol, and this is the binding. This is the stretching, right? So 3630, 3620, these are the primary, secondary alcohol. So secondary having slightly lower. When we compare the molecule, so you have to keep in mind that secondary alcohol having slightly lower frequency compared to primary. This delta means this is a bending. So it is observed around 1350 to 1260. Phenol having slightly lower compared to aliphatic hydroxy group. So this is aromatic, so it is slightly lower. Its bending is slightly higher due to the conjugation of pi electrons. So this is the list. So comparative study you can do with the help of this list. Thank you very much. for listening to me.